everyone, thanks for this opportunity to introduce the work I have done in Great Project. In this presentation, I will briefly introduce how to use Pore work model to describe hydraulic property of clay upon drying paths. First, let me introduce myself. My name is Xu. I came from Tongji University of China. During the whole year of 2016, I have this chance to join University of Strathclyde through Great Project. Here, I really want to say thanks to Professor Alessandro Tantino, Professor Weimin Ye, and Dr. Matteo Petrotti. Thanks for their support and help in this whole year. There are two research directions I am interested in. The first one is experimental research on gas migration behavior in low or ultra-low permeability materials. The second one is the modeling research on hydraulic mechanical characteristics of clay using Pore work model. Here below is my email address. If you are interested in the similar topics, please contact me. I'm looking forward to deep communication with you. Okay, first, Pore work model is widely used to describe the single or multi-phase flow behavior in porous materials. However, in previous researches, the porous medium is normally regarded as a rigid and non-deformable material. It is not a real thing for soils because during multi-phase flow, especially for drying process, soil will shrink when saturated pores drain as suction increases. Therefore, it is important to establish Pore work model with consideration of material deformation. Here, we make three assumptions before the establishment of the model. First, pores are associated by parallel clay particles. The capital letter A denotes the surface area of individual pore. It will keep constant during the whole drying process. We create a three-dimensional square mesh of intersecting pores with different diameters. Each pore is connected with 26 other pores. That means we set the correlation number equals to 26. Different from usual practice, we do not divide the pores into pore body and pore throat. Each pore can be considered as a throat to a bigger connected pore or as a body to a smaller connected pore. We used the MIP result to generate the pore network. According to a number of pores corresponding to each diameter intervals, the pore size distribution frequency can be accreted. Then the diameter can be randomly assigned to the three-dimensional lattice. In addition, a new three-dimensional lattice is created to reflect the saturation state of the pores. Here, in each suction step, we set three criterions for saturated pores to be drained. The first one is target pore is connected at least with one unsaturated pore around it. The second one is target pore is connected to the exterior boundary through a continuous pathway of air. The third one is target pore is larger than the gas entry pressure, calculated using Washburn equation or Laplace equation at the current suction step. It is clear that in the following figures, the pores number 1, 2, 3, 4 are saturated in initial conditions. However, they have different drain process according to the three criterions. For pores deformation behavior, we regarded that with increase of suction, saturated pores will shrink. Once the pore became empty, the suction will decrease to 0 kPa. Then the pore will swell again. Based on a series of derivation process, the shrinkage and the swelling behavior of pores are obtained. Using parameters determined from some other literatures, we verified and calculated the result. The top right is the pore size distribution curve from the result, and the bottom figures the calculated water retention characteristics with and without the deformation of the pores. It is clear that deformation is an important factor in calculating and analyzing this process. Thanks for your attention. Hope to communicate with you in future.